Hello YouTube, this is Eric from Coder Snacks. Today we'll talk about an interview question that, while not as algorithmically intense, requires some attention to detail: mean, median, and mode. Let's get started. Mean, median, and mode is an interesting problem to me, not because of its technical complexity, although there are some interesting parts, but because of the number of small details to keep track of to code a strong solution. It's also dear to my heart because it was the first programming interview question I was ever asked. And we'll just say it's a great reminder of how much I've improved. Let's dive into the problem. As always, we should ask some questions first. To start with, what do these terms even mean? Even if we know the terms, mean has multiple correct definitions, for example. We should clarify what the interviewer wants. For our purposes, we'll use the following definitions. The mean is all of the numbers summed up divided by the number of values we have. This is also called the average, or the arithmetic mean. The median is the number that's in the middle if all the values are sorted, and the mode is the number that appears the most often in our input. Next, what kinds of values are we handling? Both in terms of the values themselves, but also how many of them at once. As we'll see, there's a trade-off between code complexity and runtime complexity that we should consider. If our lists are small, we should go for simpler solutions, but if we're handling billions of numbers, the simple answer may not be sufficient. Another question is, what kind of API do we want to present? If we're always going to be returning all three answers, there are some commonalities we can exploit, but it's also useful to have different functions for each of these values. There are a bunch of other questions we can ask here, but let's write some code for context. One thing I would note is that these are very common math functions, and there must be good, well-tested versions in the wild already. It's unlikely that an interviewer is going to accept use NumPy as a solution to their question, but it's worth noting, if only to indicate you're not going to run off and write code for everything that's already in the standard library. Let's look at mean. This must be straightforward. There's nothing to do but loop over all the numbers, sum and divide, right? I mean, what else could you do here? Well, even in a simple, straightforward implementation, we need to be a little careful. In this little code snippet, there are at least two possible bugs. Can you find them? If you'd like, pause the video and take a look. First, since we're passing in a list of ints, and the length is also an int, that means that the division that takes place here is integer division. It isn't specified whether we want an integer result or not. If we don't, then we need to do some float division here. Second, what does this code do if we pass an empty list? Because the length of the list is 0, we get a 0 division error. What should happen? This is an interesting question, and you should discuss it with your interviewer. Are we content with just letting that error raise to the caller? We could change the error that's thrown, since with 0 division error it's not as obvious to the caller what they did wrong. Alternately, we could pass back a sentinel value, but be careful here. Normal sentinel values like -1 could legitimately be answers. You might also decide to return 0 depending on your use case. These are all great things to talk about. These aren't bugs per se, but there are some other style issues. First, many Python users consider it good style to use the implicit falseness of the empty list to check if the length is 0. Another issue with this code is the variable name sum. Sum is a built-in function in Python, and while this code works, it's better not to overwrite built-ins. In fact, we should use the sum built-in here. Let's do that. In some other languages, you should also consider overflow. For example, if we write a similar version in Java, it would be easy to write a version where we don't get the correct answer because our values are too large for variable types. What could we do about that? There are a few possibilities. We could use a type that won't overflow for our data, like a long or a big integer, for example. Another possibility would be to calculate the average as we go along, but this requires more work, an additional division in each loop, and brings possible precision issues with it. The takeaway here is, even in a very simple problem, your solution can say a lot about the way you approach coding and the knowledge you have about your chosen language. Let's take a look at median. If we're working with smallish groups of numbers, a simple way to solve this is to sort the array and return the middle element. This works fine, although again we should be careful. Let's look at a few examples. What do we mean by the middle element? If we do something like this, it works fine for odd numbers of elements, but what about even numbers of elements? What is the median for a list with even numbers of elements? Mathematically, the median is the average of the two middle elements, but there are other possibilities. This is a great thing to clarify with your interviewer. To make things a little easier for us, we'll assume that the median is the smaller of the two middle elements, but all of these algorithms can work for the average of two elements as well. So, what is the complexity of this solution? Sorting can take order n log n time, and space is dependent on whether we're making a duplicate of our list and what sorting algorithm we use. Can we do better than O of n log n runtime? Well, there's a randomized median solution that runs in O of n, usually. Here's what we'll do. Take our unsorted input array and randomly choose a pivot element. Split the array into elements that are less than our pivot and more than our pivot. Then, look at how many elements are smaller than our pivot. If that number is larger than the index we're currently looking for, recurse into the group of numbers that is smaller than our pivot. Otherwise, recurse into the group of numbers larger than our pivot. If we go into the larger than group, we have to adjust the index we're looking for by the length of the smaller than group, plus 1 for the pivot, because we've eliminated that many smaller numbers. In the first example here, we're looking for an element that's 10th smallest, and there are 12 smaller items, so we know the median will be the 10th smallest in the smaller than partition. However, if we randomly chose a different pivot when we did the split, our smaller than and larger than partitions would be of different sizes. In this example, 7 elements are smaller than the pivot, and we're looking for the 10th smallest, so we know our median has to be in the larger partition. However, we're no longer looking for the 10th smallest in the larger partition. We've already gotten rid of 8 smaller elements, 7 plus the pivot. So now we're looking for the second smallest. Finally, if our pivot is exactly at the rank we're looking for, we can just return the pivot element. If you're familiar with quicksort, this should look familiar. The difference is that instead of recursing into both halves to sort, we only recurse into one half to find a particular element. Let's write some code. First, we'll write the code to do this recursive searching. After some basic error checking, we will choose a random element from our list and try to split into 3 parts, smaller than, larger than, and the same as our pivot. Once we have that split, there are the cases we discussed above. If we have more numbers in our smaller list than our index, we recurse into the smaller list. If the number is actually the index we're looking for, we return it. Otherwise, we recurse into the larger list, reducing the index we're looking for by the number of elements that were smaller and equal to the pivot. Then we write a few more tests to roughly verify that we're getting the results we want. Looks good so far. Now that we've written selection rank, we can use it to find our median. We just figure out the index we're looking for and call our newly written selection rank function. No problem. This works on normal kinds of inputs, but just like in mean, we should spend some time thinking about whether or not it would work on abnormal input and what we would want to do in those cases. Great. What's the runtime complexity of this code? We hope it's going to be O of n. Somewhat simplistically, we think we're going to recurse into a smaller list of about half the size each time, and we do O of 1 work per element of the array to build the pivot lists, so we should end up with something like n plus n over 2 plus n over 4, etc., which is 2n, thus O of n. In reality, we won't be that lucky each time, but as long as we on average split off a decent percentage of the array, we're fine. The worst case, however, is that we happen to pick pivots each time that can only remove one element from consideration. If that happens, then this algorithm can run in O of n squared. This is the very worst case, though, and we'd have to be extraordinarily unlucky for that to happen. For space complexity, the algorithm takes O of n space, since we need to build the pivot lists. If we're allowed to modify the input list, however, we can do this in place. Instead of building the pivot lists, we would swap all the elements that are less than the pivot to the front of the array, and then loop and search further by passing indices. This has the same runtime complexity, but if it's done iteratively, it takes O of 1 space. So normally, this randomized algorithm runs in O of n, but what if we're scared about the worst case? Can we calculate the median in O of n deterministically? It turns out we can, but maybe we shouldn't. The problem with the randomized algorithm is the chance we're going to pick a pivot that only gets rid of a small number of elements, right? What if we could guarantee a certain percentage? That is, we will always pick a pivot that lets us get rid of, say, a quarter of the list. In that case, the solution could be deterministically O of n. How can we do this? In broad strokes, the theoretical solution looks like this. Break our input into groups of 5, and find the medians of all those groups. Because there are a constant number of items in a group of 5, finding the median is technically O of 1, and we do this n over 5 times. Next, pivot around the medians in each group, so on one side we have lesser elements, and on the other side we have greater elements. Next, recursively call our median finding function on all of these medians to find the median of medians. If you arrange these groups so the median of medians is in the middle, you can see that we found a pivot where at least a quarter, actually 3/10, are definitely smaller and 3/10 are definitely larger. We may actually be able to do better than that, but we know that our pivot will allow us to get rid of at least 3/10 of the numbers. Okay, let's code that up. Okay, no, let's not. It's a good idea to know that this algorithm exists, but realistically, you're not going to code it up in the space of an interview. Also, in practice, it works worse than the randomized algorithm. The algorithms we have so far require O of n space or require us to modify the input list. If we can't modify the input and we still want to use O of 1 space, there is yet another way. We start by finding the minimum and maximum of the list, and then use binary search to search. In this example, we start by taking the average of the min and max, and we iterate through the list seeing how many elements are greater than and less than this average. Then we decide if the median is greater or less. We repeat this until we find the median. This approach takes O of n log k time. We iterate over the list each time, which is O of n, and we do it log k times, where k is the difference between the minimum and the maximum. So, we can see there are a number of ways to do this, depending on your time and space constraints. Make sure to keep in mind your use case, however. The easiest thing to do here is sort and look for the middle. And if you have some small number of elements, or even 100,000 elements, this takes very little time. If you have hundreds of millions or billions, though, you should know about the other methods. Finally, let's look at mode. The easiest way to do this is to use collections.counter, but your interviewer will probably not let you get away with that. Always good to bring up common libraries, however. An important question to ask about mode: how many modes should we return? In the best case, there will be only one, but it's possible to have multiple modes in a list of numbers. What should we do in that case? For simplicity, we'll assume here that you need to return any single mode. One way to implement mode is to sort the array and look for the longest run length of an element. Since the array is sorted, all the elements that are the same will be next to each other. This takes O of n log n time for the sort, and space complexity depends on whether we do the sort in place or not. As a bonus here, if you're doing all three of mean, median, and mode, then if you sorted when you solved the median, you could reuse the sorted list here. We can improve on n log n time by using a dictionary, where the key is an element, and the value is the number of times we've seen the element. We can iterate through the array, and update the dictionary as we go. Here, we write code to iterate through the numbers and store them in a dictionary as we described. At the end, we iterate over the keys of the dictionary, looking for the highest value, i.e. the largest number of times we've seen each element. This takes O of n time, since we iterate over every element of the array once, or twice if it's in the hash table, and O of n space, since in the worst case, we have every element once for a hash table with n entries. To improve on this solution code-wise, we should use collections.defaultDict, so we don't have to do this checking if we've already seen an element or not. Also, to get a max value out of the dictionary, we can use max with a key argument, like so. These improvements greatly reduce the amount of code we write, or that we would have to maintain in the future. Finally, if we can't use O of n space or modify the list, we're stuck with an O of n squared time solution. Start with the first element and see how many times it's in the list. Then do the same with the second element, and so on. This is O of 1 space as long as we only have to return a constant number of modes. If we have to return all the modes, we could be stuck with a return size that's O of n, as we discussed before. There are some interesting problem extensions regarding streaming. By streaming, I mean that we have some method by which we're receiving values in unknown quantities, and at some points we may be asked for the median, mean, or mode. Streaming mean and mode are fairly trivial, but an efficient streaming median is quite a challenge. Additionally, if we're talking about streaming at a large scale, we might not have enough space to store the entire set of values we're being given. In that case, what could we do to get good approximate values? For example, we might want statistics about how long all of our servers are taking to serve queries. Another challenge is implementing the selection rank algorithm in place. We gave a version that constructs additional lists, but if you're allowed to manipulate the input, doing it in place is faster and uses less memory. Next time, we'll cover some bit manipulation examples. Given two numbers, find the number of bits different in their binary representations. Beware, binary representation in Python is not as straightforward as you might like. You might try implementing it in two languages, also using Java or C++. I hope you've learned something from this video. If you have any questions or comments, or things I've missed, let me know in the comments section below. And if you enjoyed this video and want to see more like it, please like the video, subscribe, or both. I appreciate it. See you next time on Coder Snacks.